All right. In my mind, Chapter 7 is as easy as Chapter 6 was difficult. So I hope that you'll be encouraged by that, because Chapter 7 is kind of a refreshing break, especially after the difficulty of Chapter 6. And Chapter 6, I do understand Chapter 6 was quite the challenge. So Chapter 7 is helps to make sense of Chapter 6, and it goes about how the periodic table is arranged and why it's arranged the way that it is. So let's talk about the development of the modern periodic table and how it comes about. So here we go. The development. First of all, it came about in the almost all of this came about in the middle 1800s. Let's go back a little bit further than that, though, because we talked about way a long time back, even in the ancient Greeks, when we talked about the guy named Democritus, who said, you know what, guys, when they were sitting around in their togas, saying, I bet there is a smallest piece of matter. And he came up with the word atomos, which meant indivisible. So he's the first one that even suggested the idea that there's something that's the smallest piece of matter. And then remember that for several hundred years they tried to find that smallest piece of matter, and then it was finally in 1801 that John Dalton found what he thought was that smallest piece of matter. So the 1800s was a huge year for science and discovery, and the middle 1800s especially, because John Dalton, in the discovery of the atom, he opened the door, and then when those gates were open, it was just a floodgate, because everyone said, oh, here we have it. And so here you have another Englishman, John Newlands. He noticed that when these elements were arranged in order of their atomic mass, there started being some repeating similarities. And then he called it the law of octaves, or the law of eighths. And then it was, since it didn't hold for all the known elements at that time, it was kind of thrown out. And then in 1869, here's your big boy right here, a Russian chemist named Dmitri Mendeleev. He is so famous that I don't know if you even watch the Olympics, but I can recall quite vividly in the last Summer Olympics that when those Olympics were held in Russia, both the opening and the closing ceremonies had a tribute to Dmitri Mendeleev and his work with the periodic table, because he found and is credited with the modern sort of development of the periodic table. And what he basically did is he laid out all of the known elements at that time, and he was an organizer, and he meticulously weighed them, and he started laying them out on a table in order of their properties, their mass, color, and he called them reactivities, so how reactive they were with water and so forth, whether they were flammable, reacted with acids, different properties, chemical and physical properties. And he also noticed the same pattern, and he went a step further, and he noticed that there were holes, whereas his predecessor didn't recognize that pattern. He recognized that instead of there being an anomaly, he said, oh wait, there's just a hole right here. Should be an element right here. And he very accurately predicted some as yet undiscovered elements, and he was bold enough to say, hey, this one's going to be this color, it's going to have this mass. Gallium is one of the very famous examples, atomic number 31. He predicted what he called its reactivity would be, he predicted what its density would be, he predicted what color it would be, he predicted many, and it was not just that one, but he predicted several other holes in the periodic table. So he called this periodicity, and there was another chemist also, but Mendeleev is the one that's credited with this. So he ordered the elements based on their atomic mass, and then he also is credited with giving them what we would now consider their modern symbols. Before, in the ancient times, they were given more characteristic symbols rather than using the Latin. Like potassium, for example, is denoted with the letter K, and everybody always asks me, well, why isn't the letter P instead of the letter K? Well, in the Latin, and even still today in almost every other country, potassium is not known as potassium, it's known as catrium with a K. So, and sodium is natrium, that's the Latin for sodium, and every other country uses those words. And so the same is true for gold, for example, is aurium, the Latin words, and that's what we still use today. And so you can see here, potassium, which is very, very reactive, would be grouped, and then helium and neon, very, very unreactive, and so on. You see that these would have some flaws. So then along comes another guy, and his name was Henry Moseley. Now I don't know if she lists Henry Moseley, but Henry Moseley was another Englishman. Henry Moseley, now when Mendeleev did his major work, that was 1869, the proton had not yet been discovered. Henry Moseley comes along, and by this time the proton has been discovered. And so since the proton has been discovered, it's called, the number of protons in an atom is called the atomic number. So Moseley is very, very famous in the scientific world for two things. He was very brilliant, and he was fairly young for sciences. So he was famous for tweaking Mendeleev's periodic table. Mendeleev had arranged all the elements in order of their atomic mass. Mendeleev rearranged things I'm very sorry. Moseley rearranged Mendeleev's periodic table just a little, and instead of them being in order of atomic mass, he tweaked it and made them in order of atomic number, their number of protons. And you recall that does not change. So that changed a few things up just a little. You'll notice, for example, that argon, number 18, has an atomic mass of 39.948. Potassium, which is number 19, has an atomic mass of 39.098. So those two swapped places, as should be, because argon is very unreactive and it belongs with the noble gases, and potassium is very, very reactive. So those two swapped places when Moseley numbered them in order of their atomic number, their number of protons, rather than their mass. The other thing that Moseley is very, very famous for is causing a big controversy, because early in the 1900s, war broke out, World War I broke out, and like many other men, Moseley was called up in the draft. And he was put on the front lines and promptly killed. And so it caused a pretty big uproar, because there were many who said that a mind as brilliant as Moseley's should never have been on the front lines anywhere fighting, that he should have been in a lab somewhere developing weapons and, working strategically somewhere, and never should he have been fighting. And so that got some of the mamas in an uproar that said, what makes his life more valuable than my son's life? Isn't my son just as valuable as any other? And so it kind of sparked a debate. So he was famous for that. And it was ultimately decided that, no one's life is worth more than anyone else's life. They're all valuable. However, if someone with a mind like Moseley, who has a scientific gift as Moseley and others did have, Einstein, for example, Fermi, Oppenheimer, those kind of people, and they could end a war quicker, or they could help our war efforts by developing new technologies, laser weapons, things like that, then wouldn't they save more lives by working in a lab somewhere or doing something like that instead of being put on the front lines? And so that's kind of became the policy, that if you had a brilliant mind like Moseley's, then perhaps you'd be better served to not be on the front lines and get killed the first, time you were in see action, which is basically what happened to him. Anyway, that was free. So this is what you would do. Here's the sample problem 7.1, which is in your book, and you're going to see that your periodic table is now divided into groups or families, and we know that families are in the same column or group. So if you have, what elements would you expect to exhibit properties that are most similar to chlorine? Chlorine belongs to group 7A, and this is on page 279 of your text. So if it's in group 7A, which is the halogens closest to the noble gases, you would just simply list all the other members of that same group or family. Those include fluorine, bromine, iodine, and astatine as well. So those are the ones that you would list. Fluorine, bromine, and iodine are the other nonmetals that are also in that group. Astatine, you see, is a metalloid. So even though it's in that same group, it's going to perhaps not exhibit the exact same characteristics as chlorine, because it's a metalloid rather than a nonmetal. So be careful about those kinds of things. All right. 7.2 talks about the classification of metals. We know about subshells, the S, P's, D's, and F's, but mostly the S's and P's are the ones we're going to concern ourselves most about in Chem 1. Those are the ones that are in the most outermost energy level. All of the others are going to be full according to Aufbau's principle. All the lower energy electrons have to fill up those lower level energy levels before the outside energy level fills. And so it's the outside energy level that's going to have partially filled orbitals. And those are the ones that are involved in chemical bonding. Okay. And then you need to know this last word on the bottom down here, representative elements. Representative elements are any of those who have s orbitals and p orbitals that are filled. So I know that you enjoy my drawing tremendously, so let me put this in drawing mode. And remember, if you have a periodic table, that this block over here is your S block, and this block over here is your P block. If you have any element that lives in the S block, this is the S block here, this is your P block, they are called representative. Representative elements are elements who have their outermost or valence electrons in those either one of those two subgroups. All right. Notice also that on this particular periodic table, which is the same one that you have, I believe yours has the names on it though. See that they have 1A, this is group 1A. This means it has one electron in its valence shell, in its outermost energy level. All of these in the same family end in an S1. That's why they belong to this 1A family. All of these that are in the 2A family, guess what their electron configurations all end with? They all end with an S2. These all in the 3A all end with an S2P1. That's because they have 1, 2, 3 electrons that in their outermost energy level, and it would move on down. These all in this 4A end in S2P2, S2P2. Add those up and you get 4, and so on. This 5A is going to all be at S2P3, S2P4, S2P5, and then this last one besides helium, this one's going to all be an S2P6, which adds to be 8. All of the noble gases except for helium have 8. That's where the octet comes in. 8 valence electrons. Helium cannot, because the first energy level can only hold 2. So helium only has 2 electrons, period. So it can't possibly have 8. All right, I hope that you understand that. All right. Please keep in mind those electrons that are in the outermost energy level are going to be called your valence electrons. All the others are going to be full. So it's only those outside the last energy level that we're going to concern ourselves with, okay? And this is what I was showing you. All of your halogens all end in the S2P5. Now look at this little N right here. See this little N? Remember what that N means. This is going to be the row that it's on, the energy level. So let's just say, for example, we're talking about iodine. Iodine is on the 5th energy level. So it would be 5S2 5P5. This is for iodine. And then you would go to its closest noble gas, which is krypton. So the shorthand way to write iodine would be krypton 5S2 5P5. Okay? It is a halogen, and so you need to be sure that these two numbers right here, 2 plus 5, is going to add to give you 7. That's why it's in the 7A, and that A means it's a representative element. All right, I hope you got that. And then right here, I don't want to spend very much time on this because I do want you to understand it, but I don't want you to make too much of it, okay? And this is saying that metals, because of the way they're made, remember metals want to lose their electrons so that they can become like a noble gas. They really don't exist as a single element or even combine to float around as a molecule like O2. They don't go around like and buddy up. Instead, what they do is they'll join like a network. And I want you to think about them as a network of people that are trying to get ahead. And so they make all these connections with other metals, or other atoms of the same metal, like a bunch of copper metals. They all get together, and they're all kind of sitting around, and here they have these electrons that they're all trying to get rid of. And so those electrons are kind of just floating around, saying, where can I be? Where can I go? Where can I go? And so those electrons are free to move around. And so what you really have is like a three-dimensional shape of copper with these electrons free flowing in between them. And so you don't have you have like this network of atoms, all right? So you don't really have a formula for copper. What you have is this shape for copper, which is a good thing because it's this loose electrons floating around, homeless basically, that allows us to have electricity and allows metals, many metals, iron, copper, aluminum, to be very good conductors of electricity and heat. And if it weren't for that, then we wouldn't have hand warmers that's made out of got iron filings in them and other things in them, and we would not have electricity, copper wiring that allows those electrons to flow through them. Okay, so I don't want you to spend too much time on that. All right, but for non-metals, carbon dioxide that we've learned how to name, water molecules, oxygen gas, the diatomics that we talked about, these we can talk about an empirical formula, okay, because they will lattice up and partner up so that they can have a real structure. And in this case, you can have, we talked about the diatomics that will so want to be like noble gases that they won't exist by themselves, that they will always have a partner. And so there are some other examples as well, like, for example, phosphorus and sulfur. Phosphorus exists as P4, and sulfur will often be S8. So they have these molecular formulas. Now, I will expect you to know the H2, the N2, the O2, the F2. I explained those to you a while back when we were writing chemical formulas. Those 7 diatomic molecules that will always be, when they are uncombined or unreacted, you've got to put the little 2 down there with them. Okay, and then the noble gases. The noble gases are very unreactive, and they are the group 8As, and they were not going to react very easily at all. Okay. And then please remember as well where the metalloids are on the periodic table. I believe we've talked about this as well, okay? We're not going to much talk about the effective nuclear charge. We're not going to talk too much about that. We are going to talk about atomic radius here, okay? And I'm going to go back to a periodic table to show you this. I'm going to mark this periodic table up pretty good. I feel sure I've already done this before, but I'm going to do it again. These these few elements right here make up what are called that I've done in purple right here are your metalloids. Remember, they have properties of both metals and nonmetals. This group right here, very important, probably the most important group on the entire chart. These are your noble gases. Okay? Then all of these that are to the left, all of these to the left are all your metals. All of them are all metals. Now remember, these in here are your transition metals. Actually, that's not so because this doesn't have this bottom row separated. These bottom two rows are your inner transition. These here are your transitions. Do they have the bottom row? This periodic table is kind of strange. No, these are your transitions. They don't have your inner transitions that are separated. Okay? And some periodic tables like this one is kind of different because it's got this 71 listed on here, and most of the time they've got these two listed anyway. Sometimes these are listed down there with the lanthanoid and actinoid series, and they've put them up here with these two, which is kind of a little bit different. Nevertheless, then down here are your inner transition. Those two rows that are at the bottom, your F ones, the ones that fill your F orbitals, and then these very few over here. Let me switch colors. These over here are your nonmetals. There's not very many of them, and also hydrogen is a nonmetal. Okay, so that's how your periodic table breaks down, and I kind of stumbled a little bit there because it freaked me out, these two that are in a different spot on this particular table. That's how it all breaks down. Now, I hope you got that, but I also want to let's talk about size of elements. And if you think about it, it really, really, really does make sense. As you go down in the periodic table, the elements tend to get larger. And that should make sense. If you're still in the same family, as you go down in a periodic table, you are adding, each time you go down a row on the periodic table, you are adding a new energy level. Think about the periodic table with me. Think about what it looks like. This is the last thing I'm going to do, and then I'm going to stop for today. As you are adding a new row. You are adding a new energy level. And each time that you're adding a new energy level, here's your nucleus, you're adding a new energy level, then you're adding a new energy level, then you're adding a new energy level. That's what's happening as you go down. Now you're going down, now you're adding a new energy level, now you're adding a new energy level, now you're adding a new energy level, now you're adding a new energy level. It makes sense that the atom is getting larger and larger and larger. As long as you're in the same group or family, as you go down the row, down the column, it's going to get larger and larger and larger. It makes sense. Okay? But what about as you're going across a period? this is one of the things that I think of. She does a great job explaining this. Okay? As you go from left to right across a period, as you go from left to right across the period, think about this. There's a really powerful attraction. You got the protons. They are in that nucleus. Every single time you're adding another proton, where are you adding it to? The nucleus. And they are acting all together. So what's happening, I didn't realize I was going for 30 minutes. Here's your protons all acting together. So each time you're adding another proton, they're all going to the same spot, like a team, all working together. And each time that you're adding another electron, you're adding it to the same row as well. But they're not working together. So you have these protons, all of them being added to the exact same spot, but the electrons not working together. The protons are. So the protons are all pulling those those electrons in, pulling them tighter, pulling them tighter, pulling them tighter. The electrons, as long as you're adding them to the same energy level, the same row, can you see with me that as you add one more proton, one more electron, one more proton, one more electron going into the same row, these guys are not helping each other, they're not working together, these protons are. So they can pull harder than these guys, pulling it in tighter. Okay? It's pulling it closer to the nucleus, making it smaller. That's why as you go across a period, across a row on the periodic table, the atoms get smaller. They get larger going down, larger going down. The size of atoms get larger going down. Look at this, bigger going down, but smaller going across to the right, larger going to the left. Okay? Larger going down, smaller going to the right. Larger going down, larger going left. Larger going down, larger going left. Okay?